Now we have a mechanism to develop any conditional distribution. We are interested in conditional probability density function. It's a little bit paradoxical because probability that x be exactly equal x, if x is a continuous type or a mixed type random variable, this is going to be equal to 0. So if you say that your event A is equal to the event that x takes equal to x, and if you say probability of any, so suppose that this is m, probability of A given m will be equal to probability of A intersection m, and then divided by probability of m, and you will get 0 divided by 0. So this is paradoxical. So to resolve these paradoxical case, and we want to have conditional PDF of one random variable given another random variable, we'll do it in a more rigorous way. So we use the method in the previous video in order to define the conditional PDF. So we are interested in to define the conditional distribution, conditional probability density function, one random variable, given that we have observed a value of another random value. So let's say the output of the channel or some parameters you observe from a patient, but you are interested in distribution of something else this is the transmitted signal, this is received signal, this is the received information, and this is the what we don't know. We want to evaluate it. So we need the PDF of what we don't know given the values that we know. So we cannot calculate these directly, these conditional probability, because probability of this guy is 0 for continuous time. So for this case, what we do, we define an event that m is random variable x being in a very small interval, and then let dx tends to 0. So so this dx this will become an interval, and then we let this interval to shrink to a small enough value. So the event m is in the neighborhood of x. So this means being in the vicinity of x, and the size of this event is dx, and this is a limiting behavior. Then we do let dx to 0, and we say that limit of d when dx goes to 0 is this event. So this, we would like to think like that. And then we write the CDF of these random variables. So basically this is going to be probability that y is smaller than or equal y, and then intersection with the event that x is bigger than x is smaller than x plus dx. So then we get probability of this one, which is going to be probability of x being greater than x is smaller than x plus dx. Obviously, the denominator itself is the CDF of x at x plus dx minus fx of x. Okay? Obviously, if dx tends to 0, these two guys become equal to each other, and denominator becomes 0. So numerator will happen. So you have a 0 on numerator, a 0 on the denominator. So this method allows us to resolve the paradox. So what we get is that denominator is equal to fx of x plus dx minus fx of x. Basically is, if you have your PDF, and here is x, and here is dx plus x. So this area is your probability. So I'm looking for this area. So this is probability of m. So this is probability of m. And probability of m, if dx is small enough, is going to be equal to this height, which is fx of x at this value, okay? So this is fx of x times this width, and this width is dx. And this is this height. So this area is equal to width times height. If dx is very small enough, this blue area is like a rectangle, so it's going to be equal to this one. So dx is height, and this one is the width. So denominator is equal to that, but nominator is also same thing. So let's see, nominator. So denominator, I get fx of x dx, and nominator, this one, is like I have a differentiation on x. If I have a function fx of x and y at x plus dx of y is fixed, and minus fx of x y of y, means that I've taken from this function fx y of x and y, I've taken two samples at this point, at this point. So I've taken samples at point x plus dx and y, and then subtract them. So I could say that this is equal to the derivative of these with respect to x, okay, times dx. Okay, so this is an approximation for that. So this is the definition of, so basically if you calculate this by dx, and if you say limit of this one when dx goes to 0, this is the definition of partial differential. So this guy, if you say, oh, dx goes to 0, the limit of this guy is this one. So if you substitute that, you get that this is equal to this. So what I have done is that I have considered a very tiny interval and then let it to be 0. So at this limit, probability of m becomes equal to that, and this guy becomes equal to that. So what I get is that the conditional distribution of m, when dx tends to 0, becomes equal to that, when dx is very small. So now I could calculate the derivative of this function with respect to y. So I want to, because this is the CDF of y given this event, I want to find PDF of y given m. Okay, so if I add another derivative here with respect to y, what I get, this is a differentiation with respect to x. I add another differentiation with respect to y. I will get derivative with respect to both x and y of fx y of x and y. So basically, this gives me the joint PDF, gives me fx y of x and y. So basically, this equation becomes equal to this one, and then I could substitute. So basically what I see, and this event, this is event m, and then dx is very tiny, goes to 0. So what I get here now is that the conditional PDF of one random variable given another one. So what I see here is that the joint distribution fx y of x and y divided by the marginal PDF, the joint PDF divided by marginal PDF fx of x gives you the conditional distribution. This is this. Or you could say that the joint distribution is equal to the conditional distribution of y given x. Sometimes I denote this one y given x of y given x, okay, times fx of x. So this is another notation for the same expression. So this is like if you had probability of A intersection B is equal to probability of A given B times probability of B. Okay, so it's kind of like that. So this is a another upgrade, another addition to the same formula, the same concept. So the conditional probability density function is something that you could write this way. Similarly, you can write conditional probability density function of x given y of x given y. So this notation means that y equal that y. This is equal to, this is a notation, f x y of x and y divided by marginal distribution of y of y. So so from here we get this general equation. So you could decompose the joint distribution as product of conditional times marginal. So this is a very simple theorem. We say that any two random variables are independent if the conditional distribution is equal to unconditional distribution. Because if this is equal to this, if you substitute that, that means that the joint PDF is decomposable, they are independent, and the other way around is easy to prove and argue. So so this is the proof is that they are independent. If you can decompose it, okay. So you put it here, and then you can conclude that f y should be equal to this one, and so on.